Good afternoon. Today we are going to see about the solution to load flow problem. So in this load flow problem, solution to load flow problem or power flow problem, all are same. Methods are available for solving this load flow or problem. In all these methods, voltage solution is initially assumed. Actually, voltage is initially assumed as 1 per unit. That is, all the power is transferring. Say, for example, it is 11 kilovolt volt in the generation bus. So what we are assuming the voltage 1 per unit, that is 1 at the rate of 0 degree. Okay, the angle we are taking as 0 degree. So it is default meaning is like all the power, is transferred. Okay, so that is the meaning. Next, initially assumed, then improved upon some iterative process until the convergence is reached. So we are going to calculate what is the real power, what is the reactive power in that particular bus, and what is the voltage, and what is the change in the voltage that we are going to calculate. So the load flow methods are as follows. There are three methods. The first method is Gauss-Seidel load flow method. The second one is Newton-Raphson load flow method. The third one is fast decoupled method. There are three methods. Say, for example, these are the algorithm. These are the certain algorithm that is given by Gauss and Seidel, then Newton and Raphson, like that, and combiningly they developed this fast decoupled method. So each and every method has its own advantage and as well as the disadvantages that we'll see later. So which method after completing all, so you yourself can able to say which method is fast, which method is slow, which method is taking more iteration. Like that, you can easily you can able to accumulate. You can able to tell at the last. Today we are going. So these are the some algorithm given by these scientists. Okay. So say for example, in future you can also frame your own algorithm and give your name. But that algorithm should really calculate your voltage change in voltage accurately. Then you can also invent a new algorithm and you can give your name. Okay, so it is not mandatory like you have to follow. So universally, this algorithm is successful model, successful algorithm. So we are also following. So nothing more than that. Okay, so you may have a question why this three algorithms. There are many n number of algorithms are there. Okay, so there are n number of optimization techniques also there. So if you feed, then but the basic formulation is this algorithm, that is Gauss-Seidel method, Newton-Raphson method. These are the some successful algorithms. There are many algorithms framed by many scientists, but these algorithms are successful algorithms, so that we are also following the same. Okay, next, coming to the Gauss-Seidel method or algorithm. So take down this algorithm. This algorithm is very, very important. So once you understand the algorithm, then everything is easy. So the following method or following algorithm or procedure is for the Gauss-Seidel method. The first step, you need to formulate the Y-bus matrix. That is nodal admittance matrix that we have already seen in our previous classes. If you are having any doubts in framing the formulation of Y-bus matrix, you need to go through my previous videos. Then you come back here. That I have explained in detail. The very first step is formulation of the Y-bus matrix for the given data given. Okay. Next, second step. Step number 2. Assume the flat voltage profile or flat start. Okay. Assume the flat voltage profile or flat start. That is, initially assume the value of voltage magnitude as 1 and phase angle as 0. Okay. So it is meaning like the full power, that is in per unit, no? The full power it is meaning like the full power, full voltage we are taking. Okay, in that particular bus, the voltage is full. Say, for example, 11 kilovolt is the generator. So we are also generating the 11 kilovolt. Like that, the meaning is. So that's why we are assuming the flat start or flat voltage profile. That is, we are taking B is equal to 1 plus J0 for all nodal voltage except the slack bus 1. For all the nodal voltage except the slack bus 1. Why except the slack bus 1? Because the slack bus already we know. Okay, in slack bus, if you go through my previous videos, in slack bus, what is there? D and delta is there. P and Q we need to calculate. That is real power and reactive power we need to calculate. So slack bus already voltage we know. So no need of calculating for the slack bus again. Okay, so this is very, very important. So don't do mistake here. Okay, slack bus. So many books they will tell like except the slack bus. So they won't tell why you are not calculating for the slack bus. Because slack bus already given in the problem. B and delta is already mentioned, so no need of following that. Next, set the iteration count k is equal to 0. So we are taking k as an iteration count. In some books, they will be following I and all. Okay, whichever the algorithm is easy, you can follow. But we are choosing the iteration count k is equal to 0. Next, set the bus count. Set the bus count p is equal to 1. Set the bus count p is equal to 1. Check for the slack bus. That is, check for the slack bus. That is, p is equal to slack bus. Increment p. Okay, so increment the p. First, you need to check for the slack bus. So you are taking the p is equal to 1. P is nothing but the slack bus and increment the p. Okay, next step number 4. For the bus p, evaluate BP power k plus 1. BP k plus 1. Okay, so this is the formula for voltage equation for this BP k plus 1 is BP k plus 1 is equal to 1 divided by YPP into PP minus J into QP divided by VPK the whole star minus summation Q is equal to 1 to P minus 1 YPQ BQ K plus 1 minus summation Q is equal to P plus 1 up to N YPQ into BQ K. Okay, the whole bracket. Okay, so take this as equation number 1. So this is the algorithm. So for calculating this VPK K plus 1. So this is the steps in the algorithm. Actually, a derivation for this also there. And if you follow the derivation little bit, it will be time consuming and also it will take more time to solve. So that's why in the algorithm directly you take this formula. Okay, you need to remember this formula and direct away you take this formula so that the time for solving the problem will be reduced. Okay, so I repeat, VP k plus 1 is equal to Y1 divided by YPP into PP minus J into QP divided by VPK, the whole star, minus summation Q is equal to 1 to P minus 1, YPQ, VQ, K to the power of K plus 1, minus summation Q is equal to P plus 1 up to N, YPQ, VQ of K. So take this as equation number 1. Next, calculate the step number 5. Calculate the voltage difference on change in the voltage. Okay, say for example, sending end you are sending as 11 kilovolt. Receiving end, what is the change in the voltage? So okay, so sending end we are choosing a 1. Okay, initial flat start we are taking as 1. In receiving end, what is the change in voltage? Maybe 0.99 or 0.95, like that change in the voltage. So that difference also you are calculating. How much? Because you know, in the power system, the buses are very far. We already seen some buses. Okay, 3 bus system, 2 bus system. For that we have solved for a Y bus matrix and all. So there in the problem, just like that, what we are doing is we are keeping the buses as 1, 2 like that. So distance between the buses, say for example in the paper while solving, so it will be like a 1 centimeter or 2 centimeter like. But actually speaking, in the real world, so distance between the buses, if you take, it may take around 10 kilometers, 20 kilometers, 30 kilometers. It depends on your own practical structure, practical path system structure. So it will be not less distance. Okay. So minimum there will be a distance is there. So there the loss is also there. So definitely there will be the loss in the voltage. That's why we are going for calculating this change in the voltage. Next step. Advance the bus count by 1 and check if all the buses are taken into account. If yes, go to the next step. Otherwise, go to the third step. Okay. So again, we need to do, we need to advance the bus count. So say, for example, second bus you are calculating. Next, we are calculating for third bus, like that. Okay. So advance the bus count. So we need to, if yes, go to the next step. Otherwise, go to the third step. Again, you need to take the bus count, like a bus count as P is equal to 1. Again, you need to calculate the VPK plus 1 for that particular bus. Okay, say for example, K is the bus count is 1. So again for, sorry, bus count is 1 or 2. So again for second bus. Okay, second bus you need to calculate. Third bus you need to calculate. Like that, similarly, you need to repeat these steps. Next, again, you need to change, calculate the change in the voltage or voltage difference. Change in the voltage you need to calculate. That is del P 2, del P2 that you need to calculate. So like that you need to calculate. Otherwise, go to the step 3. If yes means go to the step next step. What is the next step? Step number 6. Find out the largest of absolute value of the change in the voltage. The process of convergence can be speed up by the acceleration factor. See, this alpha is the acceleration factor. Okay. So this alpha we are taking as 1.6 some always. Okay. So you may get a question why it is 1.6, why can't some 1.5, 1.4 like that. You can take, but majority while solving many problems. So this if you choose this acceleration factor as 1.6, the convergence will be a little bit fast, and also answer will be somewhat accurate. So that's why it is a trial and error method. You can also choose 1.5. You can also choose 1.4. You can also choose 1. Okay, it depends on the user define. But generally, okay, throughout world, they are choosing this alpha as 1.6 for getting accurate value, and also the process will be the somewhat speed. Okay, so and so that we are going for this acceleration factor alpha is equal to 1.6. Okay, it is not mandatory to choose, but all are many problems they are choosing the alpha is equal to 1.6. So here we are also choosing the alpha as 1.6. So I'm stressing that word. Okay, next we need to calculate the updated value. Okay, VP accelerated K plus 1 or updated or new value. Okay, in some books it is given as accelerated value. In some books it is given as new value. In some books it is given as a okay, so updated value like that. Okay, so here we are using as an accelerated value or new value. Okay, so VP accelerated K plus 1 is equal to VPK plus alpha into del VP. So this is the new value. VPK plus 1 is the new value. That is VP new is equal to VP old. Okay, plus alpha into del VP. Okay, in the some books, in some materials, it will be mentioned like new and old value. Anything you can take, your own wish. But the thing is that the answer should come. That's all. Okay, you can choose any words that answer is very, very important. So here we are choosing the VP accelerated value or VP new value. Okay, so it is nothing but what is this del VP? Del VP is nothing but del P K plus 1 minus del VP K. Del V, that is the this K plus 1th value and as well as the this kth value. Say for example, iteration if you take as k is equal to 1. Okay, so it will be 2. VP 2 minus VP1, like that it will come. Okay, this is the accelerated value or the new value for formula for calculating the accelerated value or new value. Okay. What is the alpha? Alpha is the acceleration factor and it is a real number. A suitable value of alpha for particular system can be obtained by running trial and error method. So everything, say for example, in power system, sometimes we are going for trial and error method. Substitution method or trial and error method. We are substituting one value and we are seeing the answer. If it is near to that, we are taking that. Or otherwise, again, we are going to second iteration. We are taking some other values and again we are doing the same. So that is the trial and error method. So usually alpha is taken as 1.6. It is a general recommended value for most of the system. As I said, most of the system we are taking the alpha acceleration factor as 1.6. However, it may be noted that wrong selection of alpha may result in slower convergence, as I said before, and sometimes even results in the divergence from the solution. Okay, sometimes what happens is the divergence of the answers will be more. Say, for example, you are doing by taking alpha as 1.6. Your friend is taking alpha as 1.5. Okay, so if you see the answer, the voltage and change in the voltage, that will be a much difference. Okay, some 5% difference or 10% difference. Sometimes depends on the value of alpha, and convergence also will be slow. Okay, for you, the convergence will be within some 3 iteration. For your friend, your convergence will be of 10 iterations. So convergence and time taken for the solving that problem also will be more. So that also you have to be noted. Next step. So what is the step number 7? Step number 7, find the voltage for all for other buses. N, that is by taking the P is equal to 2. But bus count we are incrementing and we are taking, that is VPK plus 1. No? For second bus, we are first bus as of now, first bus completed. Again, similarly, you need to calculate for second bus, same voltage and change in voltage. So repeat the iteration till VP del VP for all the buses. Say, for example, bus count is P is equal to 3. You need to calculate up to 3 VP V3. Okay, and del V3. Okay, so 3 buses you need to calculate. Next step. This is zeta. Okay, this what do you call this? Yeah, this zeta is nothing but tolerance value that is within the limit. So using the tolerance value zeta, zeta, we are taking das 0.0001. Okay, we are taking das zeta as 0.001. So here also you may get the question, why is a tolerance value you are taking that 0.001? Okay, so if we are going for a tolerance value 0.0001 and more than that, say for example, if you add another one 0.0001, okay, so number of iteration, the iteration might be somewhat reduced. Okay, tolerance maker. The program can stop within the particular, otherwise the program will run for n times. If you choose, you can also choose a tolerance limit at 0.1 also. But the thing is that number of iteration will take more. Okay, so generally we are taking the tolerance limit at 0.0001. So for programming aspect, I'm telling the same algorithm you can program with MATLAB or otherwise Python programming also. Okay, so because the logic is given to you in any platform, even C programming or C++ programming, whichever is convenient to you, you can program it. Even Python also, it is very easy. So you can program it. Okay, so but the tolerance limit, if you give 0.0001 or more than that, your iteration, number of iteration will be that you will within the less number of iteration, you will get the answers quickly. Okay, so that is also there. That is VPK plus 1 minus VPK. Okay, So modulus of VP k plus 1 minus VP k is less than tolerance. Then evaluate the line flows. Then if it is less than, then the program will stop. Evaluate the line flows and print the voltage and line flows. Okay, if not, if it is this condition not set, if it is not equal to that, not greater than, less than or equal to tolerance limit, again you need to advance the iteration by k is equal to k plus 1 and go back to the step 3. What is the step 3? Same thing, same story. Again, we need to calculate the VP k plus 1, then del VP, everything we need to calculate. Okay. Then you need to calculate it again. Okay. If the system with the PV bus, then then PV is known, then Q and delta is unknown. So you need to calculate the reactive power also. Reactive power, okay, QP calculated value also. Okay, so QP calculated or QP new is equal, QP calculated K plus 1 is equal to minus of imaginary of VPK star summation Q is equal to 1 to N YPQ BQ K plus 1 plus summation Q is equal to P up to N YPQ BQ K. Okay, so this is the formula for calculating the reactive power calculated value. Okay, previously you have seen like a real power, that is PP calculated. Now we are going to calculate the QP calculated. Okay, reactive power calculation also we need to do. So it is the minus imaginary of this formula. Okay, next step. If QP calculated K plus 1 is less than or equal to Q minimum, then set QP is equal to QP minimum. Okay, the same thing we did it in our economic load dispatch problem. Okay, so if you go back to my previous videos in economic load dispatch problem also the same. If the limit is not satisfied, okay, if the limit is less than that, we are setting the power generation to its respective limits. And if the limit is greater than, we are setting the that power generating limits to its maximum power generating values. Okay, so same thing we did it for the economic load dispatch problem also. So if you are having doubt in this, you go back to my previous video. So that also we solved in detail. So here QP K plus 1 is less than or equal to Q minimum, then set the QP to its minimum operating limits. That is QP minimum. If QP K plus 1 calculated is greater than QP Q maximum, then set the QP to its maximum operating limits. So this you need to understand. So from the specified value of PP and PP, that is real power, and set to the QP, okay, calculate VP K plus 1 and find the VP acceleration value and proceed to the next bus. So you need to, okay, so for the from value of PPQ, so and value for QP and calculate VP K plus 1, VP K plus 1 accelerated, that is new values. And we need to proceed the next one. This thing has to be repeat. Okay, the same algorithm has to be repeated. So this is the algorithm for all the things. Say for example, for if you are calculating with a pen and paper, also this same algorithm. If you doing the programming, also the same algorithm. Programming is very easy. First, you need to formulate the logic for this Y bus. Okay. How Y bus already we have seen. Okay, so Y11, Y12, Y13. Okay, self like admittance and mutual admittance, how to calculate like that already we have seen. Next, the flat start, you need to program with this iteration count. Okay, so you need to formulate the loop for iteration count and for bus. Okay, and you need to feed this formula and with this iteration count. Next, to calculate the change in the voltage. Okay, and we need to find out the VP accelerated value. Okay, so VP accelerated, that is new values, VP new K plus 1. So from this formula, next is the thing is that we need to choose the alpha. There's here alpha is there. Na? Alpha you need to set alpha is equal to 1.6. That is user defined. In programming, you can type alpha is equal to 1.6, or otherwise you can give it in directly in the program also. That is your own wish. Okay, because you are the user, you are going to program. Based on that, you can program as well. Okay. Next, we need to repeat for all the buses. Bus count we need to increment. In one for loop we need to keep bus count. So we need to set the tolerance limit as this. Then only program stops. Okay. So if you compass, automatically program will stops. Otherwise, your program will be run for. So print this results. We change in accelerated value and new value. So that okay. And if the PV in the PV bus, if the P and B values are known, and Q and delta value you need to calculate. So in that particular case, you need to calculate the QP K plus 1, the formula you need to feed. Okay. Similarly, the change in the angle, power angle, that also you need to